Great pleasure to welcome the next speaker, Elizabeth Itz. And the talk is on the Riemann-Hilbert approach to the Elastodynamic Equation for the plane, connection formula between the Rayleigh waves along vertical and horizontal parts of the board.
First, I want to mention the 2 minutes.
All right, sure. Absolutely.
First of all, I want to say thank you very much to the organizers of this fantastically organized conference. And it's a great pleasure to be in Cambridge. I wish only it were a little warm. Okay, anyway, I am going to talk about Riemann-Hilbert problem, Riemann-Hilbert approach to the elastodynamic equation. It's a long-standing joint project with Alexander, and in fact, some parts of this project have been reported here in the Isaac Newton Institute in the pre-pandemic time. And we only don't remember how many times, at least once for sure in 2018. So we are solving the elastodynamic equation, two-dimensional elastodynamic equation, in the media with parameters lambda, mu, and rho, or alternatively, the combinations of those H and L. And here, U and V, W is the X and Z components of displacement, respectively. So we are solving this equation in a quarter space. X is positive, Z is positive, Z is pointing up. In the stress-free boundary conditions, with the stress-free boundary conditions. In this form, the boundary conditions, the given right-hand side parts, we could think about them as a kind of incident wave. The solution, of course, must satisfy the Zimmerfield irradiation condition, which is given in terms of Lamé potentials tau1, tau2, which are a certain combinations of the derivatives of displacement. In fact, in terms of the Lamé potential, the elastodynamic equation could be split into two Helmholtz equations. It means the equation is separable, but it is related via the boundary conditions. We are using, for the solution, the Tanasis focus ideas about the possibility to apply Riemann-Hilbert technique for linear equations. Because we started the project very soon after Tanasis focus came up with these ideas, we are using now a little bit old-fashioned original terminology about Lax pairs and global relations, not the new, modern, unified transform terminology. So the idea is, instead of solving the initial, say, Helmholtz equations, we switch to an auxiliary system, linear system for the auxiliary function and the auxiliary parameter G, and solve this system. This system is the Lax pair of the corresponding Helmholtz equation, and the compatibility condition of this system is equivalent to the equation. So we start integrating this system. I forgot to mention that actually the auxiliary functions phi satisfy certain asymptotic conditions, and the second among these conditions is used to go back from the auxiliary function to the Lamé parameters. So we start integrating the system. That's here, it's the second Lax pair for the second Helmholtz equation. Everything is absolutely symmetric. So we start integration, and we rewrite a little bit differently the system itself, and the solution is now presented in terms of the line integral of a certain I could say, conservative vector field. It's conservative because we could show using the system that the complete differential of the integrand is 0. So it means that when we write the line integral, the result does not depend on path, and we use several possible paths of integration to write several particular solutions, which are given by these integrals. These particular solutions are analytic on a certain regions of the Z-complex plates and on the border of analyticities, of the particular solution, we could write the difference between one and another particular solution, like on the top. And it is absolutely clear that the difference of two particular solutions of non-homogeneous equation is the solution of homogeneous equation, and the right-hand side part is the solution of homogeneous equation, where the jump function rho practically plays the role of a constant. So, as soon as we wrote this equation, we could use it for any x and any z. And we're using this equation for the x and z, for which we have the boundary conditions. In that way, we hope to express the jump function rho in terms of the given boundary data. If we manage to do it, then the solution of the auxiliary system can be written via the Cauchy integral on a certain oriented contour, or taking into account the second asymptotic condition, we finally could write the Lamé potential, say tau 1, in terms of the jump functions. The unfortunate truth is that that's the actually contour of integration, which could be derived from the regions of analyticity. The unfortunate truth is that we could express the jump functions rho to 1 and 3 to in terms of the known function f a known function f, but also a set of unknown functions which could not be expressed in terms of the boundary conditions. So, we need something, and this something is the second component of Tanasi's scheme, the global relation, to actually decrease the number of unknown functions, decrease and eliminate the number of unknown functions, and to write the jump conditions. So we write the global relation in the region of the complex plane Z, where two of the particular solutions are analytic. So it means it is in the region 1/4 inside the circle and another quarter outside the circle of the region. There, finally, we could write the relation between the known function and the combination of the unknown function. So, absolutely the same approach is used for the second Helmholtz equation and the second Laplace Lux pair, and finally we come up also with the set of 4 unknown functions and 2 known functions, and the total number of unknown functions is now 8, so we need to do something about that. On top of the global relation, actually, I want to mention that this same relation between, between the unknown functions for the second Lux pair and the first Lux pair, it's global relation. It's also written on a certain circular part of the contour. So it means we have it in the region where two particular solutions are analytic, and in the regions where the radiation condition gives us the same equation. So now our next step in the work to reduce the number of unknown functions is to use the joint uniformization of the first and second Lux pairs. We are choosing the new complex plane and move both solutions to this complex plane. And this complex plane is chosen based on the fact that we want phi1, phi2, and psi1 and psi2 functions be the same. That gives us a certain map, and the map transforms the contour in this way, and that's what I was talking about, the same phi function. As a result, we obtain the set of now 6 unknown functions, which describes the solution. And in terms of this new zeta complex plane, the global relations represent two system of two equations. And at that point, I want to say that this system of global relations is actually the basis for setting up a new auxiliary Riemann-Hilbert problem, because certain symmetries in this problem, they allow us to multiply the global relation, to move the global relation to the whole complex plane. So as a result, we again have a set of functions, could have a set of functions, and set up a new vector Hilbert problem. It is the problem with a shift, and it could be posed on the torus. And actually, exactly this part of our solution was reported here before. The point is that factorization of this vector Riemann-Hilbert problem on the torus with the shift creates certain difficulties. And so far, we have not been completely successful in solving this, in overcoming these difficulties. That's why we are trying different ways how to use the system of global relations, and specifically, we are going to use these global relations to find the connection formulas which are announced in the title. So now it's kind of the second part. So now we are deriving the connection formulas. And to do that, we consider a horizontal part of the contour K. Why only this horizontal part of the contour K? Because it will become very soon clear that exactly this part is playing a key role in generation of surface Rayleigh waves along the borders of the quarter space. So, as I said before, the global relations could be extended to the whole complex plane, but in our case, we are only using only one of those symmetries, and we are moving the system of global relations to the horizontal part of our contour using that symmetry. And moreover, we are writing now the system of global relations is the system for the unknown functions phi1 and phi2, expressing them in terms of phi3, phi4, and psi3, psi4. But the fact is that in reality, the functions phi3 and phi4 could be given in terms of phi3 and phi4 under the certain map. So that's the map, and the properties of this map are described in the following picture. And as a result, we might say that finally we have the system where the phi1, phi2 functions are expressed in terms of only phi3 and phi4 functions. Next, we notice that it is actually possible to do not only that uniformization which we did, moving phi1, phi2, psi1, psi2 into the same functions. We could use similar joint uniformization, moving now function 5, 3, 5, 4, and psi 3, 5, 4, making them the same. And this joint uniformization allows us to change the contour of our contour in the following way. And finally, that's the description of the uniformization. And finally, we obtain a new system of the unknown, new set of unknown function phi 3, phi 4, which are equal now with psi 3, psi 4, and we could still express, we could still use the global relations on this new set. Finally, we proceed more or less in the same way as before, only we consider these global relations not on the horizontal parts, but on the vertical parts of the contour. So we move them to the vertical parts of the contour, and we write the system expressing the unknown 5, 3, 5, 4 functions in terms of phi 1 and phi 2 functions, plus, of course, everything what we still carry and what is known like these functions which are expressed in terms of the boundary conditions. So it means, finally, we have two systems because this second system also could be in these two terms, could also be written in terms of F1 and F3. And we have now the system which express phi 1, phi 2 in terms of phi 4 and phi 3 functions, and vice versa, the system of phi 3, phi 4 functions in terms of phi 1 and phi 2 functions. Moreover, when we look at the determinants of these two new systems, we actually see that one of those determinants, it's exactly the same determinant we were using in one of our test half-plane models, and the second could be related to that determinant by the following condition. The fact is that both these determinants under certain transformations could be written as the famous Rayleigh equation for the velocities of Rayleigh surface waves. So that equation, Rayleigh equation, it is known, it has actually 4 zeros, but in reality only 2, and it means that actually both determinants could have zeros, and respectively the function phi1, phi2 could have poles on 2 parts of the horizontal and vertical contours. So, and of course the Rayleigh waves, they are generated by the poles of the row functions. So we have 2 poles for the horizontal parts, 2 poles for the vertical parts. But we also have the surface wave radiation conditions, which allow us to find the proper zero, correspondingly the proper pole, which produces the unique Rayleigh waves. So, and after certain transformations, we could finally write our Lamé potentials in terms of the residues of the jump functions, this one and that one. The first comes from the first joint uniformization, the second from the second joint uniformization, and the same about the second Lamé potential also in terms of 2 residues. So, moreover, we could do certain simplifications and introducing the notation C notation for the residues of phi1 and phi1, phi2, phi3, and phi4 functions. We could express our residues in the terms of those one, and now we are doing the last step. We are writing the connection formulas. We expect that the main contributions to the function phi1 and 2 and phi3 and 4 would come from the principal parts of the fall. That is, we assume that we could write the following representations for these functions in terms of the residues, and we substitute these representations into our systems. And finally, we obtain the certain already formulas which we obtained from just simplifications, formulas, this one and that two. And the most important, we finally obtain the connection formula between the C2 and C4 solutions which are responsible for forming the Rayleigh wave along one side of the corner and another side of the corner. And these formulas are presented here on this slide. Thank you.
Perfect. Questions, please?
So how important is the right angle in your approach?
I have hearing
Okay.
aid, you have to.
How important is it for your angle to be 90 degrees?
So we have, well, we are solving in the corner. We
Yes.
have, God knows what coming. So,
Yes. But what if you have a...
Yes, you know, it's a quarter space.
Yes, but
It's a
what
quarter
breaks,
space.
what breaks down?
You see, it's difficult enough for the quarter space. We, of course, tried for certain Helmholtz equation to make the larger than 90 degrees and smaller than 90 degrees angles, but it was possible. We actually wrote certain formulas for this case for the just one Helmholtz equation, but not the combination of two Helmholtz equations related by the boundary conditions. Currently, so far, we could not move from this model to a more advanced model, we hope, but
That's already, yes. Thank you.
That might be formulated differently. Can you progress further than the competitor methods for 90 degrees or not, or how that compares this approach based on focus method, right? Unified transform or some predecessors versus competitors. Maluzhin's approaches. I know people have worked, as you probably know, right?
Frankly speaking, we still haven't done any kind of numerics using these formulas, so we plan to do this. But so far, I cannot compare with neither Hudson results, neither nor who else was also right. Well, there are several models which allow to write.
Budayev did it, Babbage and Company, and our friend Larissa, right?
That's right.
Essentially, Maluzhin's representation, then you have reduced the problem to a coupled system of functional equations. You do some other kind of tricks, you reduce it to integral equations, regularize them, and eventually have to do numerics in one way or other, right?
Well, of course, eventually you see for many problems, finally we must switch to numerics.
Right.
We still hope that finally we will maybe using already some experience with these joint uniformizations. We will manage finally to solve the that vector Riemann-Hilbert problems and to write the exact solutions. So we hope so, and we are moving to this direction because we kind of approach it from here, from here.
Because you can progress further analytically, right?
So far, no exact solution, no numerics.
Your analytic results represents clear
Our
progress,
goal
right, or not?
is absolutely analytic approach. That's our goal, but we are trying everything what we could.
Just
Okay.
maybe I make some short comments since I was there. So about your question, Rayleigh. So in fact, there is we suspect, and we discussed it a lot with Misha-Lyalinov, we suspect that this element of focus scheme global relation should have in this application should be related to Maluzhin's equation. So we are just trying to find the connect. We were sure, and especially when we try to do this arbitrary angle, this is absolutely where it should show up. So there is still, because now it is the boundary condition are not very well separated in this case as it is in this.
So I'm kind of optimistically looking at this. For Maluzhin's approach, right angle or not does not really matter.
Yeah, of course.
But for you, it matters. Maybe
For us,
optimistically, it allows you to progress.
It's much harder than Maluzhin's problem. It's an order of magnitude harder.
Right.
We know that.
No. Mallusion is approach for elastic wedge. That's what I mean, right?
Yes.
As pursued by
Yeah.
people over the years.
Yes. No, this is also two kind of fundamental direction we see in this our project. It is the first, of course, to move to arbitrary angle and simultaneously to discover possible relation to Mallusion's functions, to Mallusion's equations. And second, indeed, after all, we have some integral equations from our Riemann-Hilbert on the torus. So just numerics, who knows? Maybe those equations already would be good. And of course, kind of number 3, where it is matrix in that equation on the torus. It is algebraic. So just like I told in my talk, we might factorize this matrix by theta functions on the covering of those. Who knows? This is. But unfortunately, that problem is also actually a Riemann problem with the shift. So it's made of course, and it is not Riemann shift. It is not involution. So you cannot really kind of get rid of the shift.
Thank you.
Thank you.
Can I suggest you thank the speaker?